Welcome to Lecture 29, in which I'm going to introduce a new concept, which is actually pervasive in physics. It's the concept of the field. I'm going to introduce it for electricity and also for gravitation, but my colleagues who study very advanced subjects like quantum field theory use the field concept, or we talk about Einstein's field equations in Einstein's theory of general relativity. So this is a very broad concept, and this will be your first introduction to the idea of field. Let me remind you what we did in the previous lecture. We looked at the electric force between two-point charges. So imagine I have two charges, negative charge, positive charge. I hold them here, and they experience a force. In this case, since they're opposite charges, it's an attractive force, and they accelerate toward each other, for example. So what's happening is I'm imagining that one charge somehow reaches out across empty space and pulls on the other charge, yanks it toward it, or if they were like charges, they would be repelling. Same idea. A charge somehow reaches out across empty space, and action at a distance acts on something distant. We think the same way about gravity, or at least we did back in Lecture 13 when I introduced gravity. So here I have this bowling ball. And what I imagine happening is right now the bowling ball, somehow all of the material that makes up planet Earth is somehow reaching out across the space between here and the bowling ball and pulling down on the bowling ball. That's the concept, so-called action at a distance. An object can exert a force on a distant object across empty space. That's a concept that turns out to be very problematic in physics. It's problematic philosophically because how can a distant thing know what's going on somewhere else? It's a problem for Einstein's relativity because it sort of implies that information and influence can propagate at faster than the speed of light instantaneously. We'll see later how that's a very big problem in Einstein's work. So we need to move beyond, we need to move philosophically beyond this idea of action at a distance. And the field concept is going to be what lets us do that. So let me imagine instead, for the case of gravity, instead of thinking of the Earth as reaching out and pulling on this bowling ball, or the Earth as reaching out and pulling on the moon to hold it in its circular orbit around the Earth, let me imagine instead that the Earth gives rise to, in its vicinity, something I'm going to call a gravitational field. And when you first hear this idea, it sounds like I'm just introducing extra complications. But in the course of these lectures on electromagnetism in particular, you'll come to see how physicists view fields as every bit as real as matter. In fact, in some ways, not as distinct from matter as you might think. So I'm going to introduce this idea of a field. At first, it's going to feel very artificial, but it's going to grow on you. For the gravitational field, the idea is Earth creates in the space all around it a gravitational field, and that gravitational field reaches out and pulls on this bowling ball. And it pulls with a force. At this point in space, there's a gravitational field, and if I put the bowling ball there, the bowling ball experiences a force of, in fact, in the case of gravity near Earth, 9.8 newtons for every kilogram. So if I want to know the force on this bowling ball, I talk about how many kilograms does it have, and I multiply it by the strength of Earth's gravitational field, which is 9.8 newtons on every kilogram. If instead of the bowling ball, I put the softball at that same point, it will experience a force which is also its mass, which is much less, times the gravitational field in newtons per kilogram, multiplied by its number of kilograms, and I'll get the force exerted on it. And we can talk about the field concept whether we talk about gravity or electricity. So if we talk about the field concept, the old view is action at a distance. The Earth somehow, in this case I'll use the moon as an example, reaches out across empty space and pulls on the moon. So there's a picture of the Earth, there's this interaction between the two of them, obeys Newton's third law, and so forth. The two are exerting forces on each other at a distance. The new view is the field view. In the field view, the Earth creates a gravitational field that extends throughout space, and what the moon responds to is just what's going on in its immediate local vicinity. The field unit, again, is newtons per kilogram, the amount of force per unit of mass we put there. The force is therefore the mass times the gravitational field. I've put vectors on these things because both the field and the force have direction, they're vectors. And so here's what the picture looks like now. I have the Earth and the Moon. The Earth creates this mysterious kind of field around it. I've indicated by shading that the field is stronger nearer the Earth because the strength of gravity falls off as the inverse square of the distance. And over there is the Moon. And the Moon doesn't know anything about the Earth. What it does know about is the field in its immediate vicinity, and there's a vector indicating the direction of that field. That's the concept of the gravitational field. We're going to apply the same thing now to the interaction between electric charges. So again, instead of thinking that my negative charge exerts a force on the distant positive charge, I'm going to say instead that the negative charge creates a field in the space around it and the positive charge responds. Equivalently, the positive charge creates a field in all the space around it, and the negative charge responds to the field in its immediate vicinity. So we replace action at a distance with this additional new concept of the field. So here's what it looks like in the electric case. Consider, for example, a proton. A proton, positive charge, is going to create an electric field in the vicinity of itself, in fact, spinning throughout all of space in principle. And an electron that we wanted earlier to say, well, it experiences a force from the proton. No, it experiences the electric field in its local vicinity, and it then responds to that electric field. The value of the field, or the strength of the field, is measured in newtons per the thing that feels electric forces, that's charge, so newtons per coulomb. Just like the gravitational force was newtons per kilogram, mass being the thing that is involved with gravity, charge being the thing that's involved with electricity, the field unit is newtons per coulomb. The electric force on a charge Q in a field E is therefore QE. The electric force is simply the charge times the electric field it experiences, just like the gravitational force was mg, the mass times the field it was responding to. So that's the concept of the field. And the field is really a big, important concept in physics, and it sounds right now, again, like I've introduced something extraneous, but the field concept is crucial, and it's going to grow on you, and it's going to acquire a reality of its own. And let's do a quantitative look at the field in particular of the simplest kind of system we know of electrically, namely a point charge. So here's a situation in which I've got a point charge Q, a point charge capital Q, there's some distance r apart. This is exactly like what I was doing in the previous lecture. And in the old way of looking at things, I would say, oh, there's a force on Q due to Q, and I would calculate it with Coulomb's law. There it is. F is K, little q, big Q over the distance between them squared, and the direction is away or toward, depending on whether the charges are similar or opposites. So there's the old way of doing things. What I want to do now is abstract away this charge and talk about what's going on just at this point because of the presence of little q, regardless of what charge I might want to put there. So I'm going to abstract away this problem about a force between two specific charges and ask instead, what's the influence that this q creates in space all around it, particularly at this point? So I'm going to take away q, and I'm going to replace a force with a field, which is there whether or not I put any charge there. And if I happen to put a charge there, it will experience a force due to the field at that point. So how do we work on this mathematically? Well, the field is the force per unit charge. Just like the gravitational field was the force per unit mass, the newtons per kilogram, the electric field is the electric force per unit charge, the force per coulomb. Well, we had a force of K little q, big Q over r squared acting on big Q when it was here. We just abstract away big Q, divide by the particular charge we put there, and there's the strength of the electric field at that point. It's just like Coulomb's law, except it doesn't have that second charge, because that second charge is sort of latent. We can put anything we want there, any other charge, and that would give us the force on that charge. So there's the force per unit charge at Q's location. And if I wanted to picture this field, instead of drawing that vague kind of density varying shading that I did on the previous slide, I can be a little bit more precise. I can draw instead vectors at every point representing this field. That is the direction and magnitude of the force per unit charge that I might put at any point. So here is a charge Q, the same charge Q. Nearby, these field vectors are fairly long because the electric field falls off as the inverse square of the distance, just like the electric force that it came from did. Further out, those field vectors are weaker because the electric field falls off with distance, and so they get smaller. There's a better way, though, to talk about that picture. I don't want to draw lots of field vectors. Instead, what I do is the following. I say, okay, let me start at some arbitrary point, and let me figure out which way the electric field points. In this case, it's pointing radially outward from the charge. Let me move a little distance in that direction. And let me ask again, which way does the field point? It's still pointing radially outward. And so I go a little further in that direction, and I just keep doing that. And then I go to other points, and I draw a straight line that heads out in whatever direction the direction of the field is in this case. And for a point charge, I get a very simple result. I get field lines that start out at the point charge, and they move radially. They don't move, but they extend radially outward, in principle, all the way to infinity. And notice something else about them. The field lines are getting further apart. And I'd really like you to picture this in 3 dimensions, in which case they're expanding outward in 3 dimensions. And the density of field lines, if you want to be really precise, the number of field lines that's crossing some kind of area is getting smaller and smaller. And in fact, that density of field lines in this picture reflects the strength of the field, and the direction of the field line at a given location gives you the direction of the field. And this should sound a little bit familiar if you think back to lecture 20, when we talked about the velocity field of flowing liquids. We drew a picture of a river, and we drew velocity vectors in there, and then we replaced them with so-called streamlines that were, in fact, the field lines of the velocity field of that flowing liquid. These are the streamlines, if you will, of the electric field. The electric field isn't anything that's flowing or moving, but these lines describe the direction and the magnitude through their density of the electric field. And we're going to use field lines extensively because they give us a really quick, good way of looking at an electric field and seeing how the electric field behaves. So I'm going to move on to a more complicated idea, but I want you to have in mind now what the electric field looks like. The electric field is this pattern of lines that give you the direction of the force that would be exerted on a charge, if you put it at that point, on a positive charge. Because of the minus sign on a negative charge, it would feel a force opposite the field. But they give you the direction of the field, and their density, the number of them crossing a unit area, to be precise, gives you the magnitude of the field. So that's the field of the point charge. So let's look now at a more complicated charge distribution. More complicated distribution is called an electric dipole. It's a really, really important charge distribution in physics. It's 2 point charges of equal magnitude but opposite signs. So imagine these 2 charges are equal in magnitude, and they're somehow stuck together on the end of a stick or something. So they make up a system that has 0 net charge, and yet it does have 2 charges in it, and those 2 charges are located at different places. They're slightly separated. So there's a picture of what a dipole might look like. A positive charge and a negative charge stuck together somehow on the end of a stick. Never mind how they're stuck there. You could actually make one that way by sticking positive and negative charges on a stick, but nature has a way of making dipoles. It's the simplest charge distribution that has no net charge. And most importantly, it's a metaphor for many molecules. When chemistry students ask me, why do I have to take electromagnetism? Well, the answer is because all the molecules they're working with, or most of them, are essentially electric dipoles. Why do we have to learn about dipoles? Because dipoles are a metaphor for molecules. If you understand dipoles, you understand much of the behavior of molecules. Here's an example. There's a picture of water. It has a negative charge associated with its oxygen and positive charges associated with the 2 hydrogens that make up H2O. The exact distribution of charge is a little more complicated than this suggests, but you can see that that looks electrically approximately like negative charge above, positive charge below. And water, in fact, is a very strongly polar, that is, it has a big dipole effectiveness. It's a dipolar molecule, and that accounts for a lot of water's properties, in particular the fact that it's a very good solvent. So that's the dipole. That's what a dipole is, and I'd like to take a quick look at the electric field of a dipole. What does the electric field of a dipole look like? So we're going to try to figure that out, and that will give you a better feel for how you develop this picture of electric field lines. So here's a picture of a dipole, just like I had on the previous slide. And let's go to some point here near the top right at which we're going to begin by asking ourselves, what is the direction of the electric field at that point? So let me first draw an arrow that is the field at that point associated with the positive charge. We're fairly near the positive charge. The positive charge is positive. The field points away from it, so I've drawn a fairly long arrow. Let me do the same thing for the negative charge. The negative charge is further away, so the field is weaker because it falls off as 1 over r squared, and because the charge of the negative charge is negative, the field points toward it. So there are two field vectors. Because the force obeys the superposition principle, I can vectorially add two forces, electric forces. I can also vectorially add two fields, and there is the net field line, and that gives me the local direction tangent to the field. Now, what I need to do is move a little ways in that direction and redo the process. And you can imagine a computer would be very good at this. I'd get bored with it very quickly. So I'm going to imagine I've moved along. Eventually I come to another point, and you'll notice I've drawn a little curved arc in there, which indicates that the direction of the field is in fact changing. And then I draw a couple more vectors, one pointing away from the positive charge, one pointing toward the negative charge. They've got the right direction. They're scaled as the inverse square of the distance and so on. I find out the net field from those two. I move a little further in that direction. And now I keep repeating the process until I've moved in to make that arc-like pattern. That's part of a field line. I didn't start right on the charges, but if I started right near the charges, you can see how that arc would extend back. So let me do that. And now I have a single field line starting from the positive charge, going out in that arc-like structure, and returning to the negative charge. That's what the field pattern of a dipole looks like. That's only one field line. There are infinitely many field lines. They're all over the place. And so I'm going to draw a few more just to give you a sense of what the dipole field looks like. So there's the dipole's field. I won't prove it, but the dipole field at large distances actually falls off as 1 over r cubed, faster than any point charge field because the dipole has no net charge. Okay, so we understand now a field of a fairly simple but nevertheless really important charge distribution, the electric dipole. And I want to take you through an interesting exercise that is going to help us to recast Coulomb's law in a very much more abstract but powerful way. So let's begin by looking at some simple charge distributions. I have a distribution consisting of a single positive point charge Q, and I'm going to adopt the convention that a charge Q has 8 field lines associated with it. There are always infinitely many field lines, but if I want to draw it, I've got to adopt some convention like that. So on the upper left, I have a charge Q with 8 field lines. In the middle, on the top, I have a charge 2Q, and so it's consequently got 16 field lines pointing radially outward. On the right, a charge minus Q, it's got 8 field lines, they're pointing inward. Down below, I've got the field of 2-point charges Q. That's a distribution we worked with in the previous lecture, and I have worked through that same process I did for the dipole to draw its field lines. In the middle at the bottom, I've got a dipole, and on the right, I've got something consisting of two unequal but opposite charges, minus half Q and plus Q. And I want to do a simple exercise with these pictures. I want to draw around them these loop-like patterns. Now picture this in 3 dimensions. This is a surface in 3 dimensions, and those field lines are pointing out in all directions. And I want to ask the question, how many field lines go through that surface? And the answer is obvious. It's 8. You can count them. Draw a different shaped surface that completely surrounds that charge. Look at it again. You'll find 8 field lines go out of that surface. Draw another surface. This one doesn't happen to surround the charge, and you can see as many field lines go out of it as come into it. And if I count a field line going out of it as positive and one coming in as negative, no net field lines go through that surface. Do the same thing here, 16 field lines. No field lines, because I've got as many going out as going in. Do the same thing here. I've got minus 8 field lines because they're all coming in. You're getting to see a pattern. Do it again down there. I've got no field lines emerging from that. Some come out, but some go in, and they cancel each other out. On the other hand, draw some kind of surface around that single charge plus Q, and you see 8 field lines going out. Other one, you see 8 field lines going out. Draw a surface around the entire charge distribution consisting of 2Q, and you see 16 field lines going out. Draw a surface around that charge in the dipole, and you see 8 field lines. Draw around the opposite sign charge, and you also see 8 field lines, but they're going the other way, so it's negative. Draw a surface around the entire dipole, and you see 0 net field lines. If you count those field lines, you'll find as many going out as coming into that surface. And finally, for this equal or opposite but unequal charges, there's a charge Q, you got 8 field lines going out. There's a charge minus Q over 2, you got 4 field lines going in. It all makes sense. Draw one around the whole system, and you've got 4 field lines, they're going out. All of these reflect a very simple fact. The simple fact is this. The simple fact is that the number of field lines that emerge from any closed surface depends only on the enclosed charge. That's a statement of something that's called Gauss's law, and although it's not at all obvious to you right now, that law is exactly equivalent to Coulomb's law. That law describes the inverse square law. That's the reason the field lines spread out in space the way they do, and the fact that you don't pick up any new field lines except where there is charge. Mathematically, I'm going to go a little higher in math than I usually do in this course. I'm going to write a calculus expression. I'm not going to do anything with it, but I'm going to simply say the expression on the left-hand side is sort of a mathematical surrogate for this idea of number of field lines, and it talks about the number of field lines being proportional to the enclosed charge and nothing else, and that's the Q sub enclosed there, and you see some constants, 4 pi and the Coulomb constant K, which we're not too surprised to see. I guarantee you it's equivalent to Coulomb's law, and it also provides an exquisite test of the inverse square law for the electric field. So there's another way of expressing what was expressed in Coulomb's law. And I want to end with a rather elegant example of how Gauss's law shows you something very important about the behavior of materials that we call electrical conductors. What's an electrical conductor? Well, a conductor is a material in which charges are free to move. Metals are conductors. Ionic solutions like sports drinks or ocean sea water. Plasmas, hot ionized gases, shown here in the sun's corona, are conductors because they got free charges. Semiconductors that make up your computer chips. And finally, substances called superconductors. Here one's shown floating over a magnet that conduct electricity with no loss of energy. And electric fields, of course, exert forces on charges. And so if I have a conductor and I let it come to equilibrium, so I let everything move around like it wants to until it stops, charges aren't moving. That's the definition of equilibrium. And therefore, there can't be any electric field inside a conductor if it's in equilibrium. If there were, charges would move. This is almost a semantic thing. If I have a conductor and it's in equilibrium, there's no electric field inside it. And let me take that fact and use Gauss's law to prove a very elegant result. So let's go to the big screen where we do quantitative things. This one isn't quite that quantitative. It's more a conceptual proof. So I'm going to do a Gaussian proof of this statement. If I have a conductor in equilibrium, any excess charge must lie on the surface of that conductor. Why do I know that? Well, I've just shown you that by definition, essentially, if a conductor is in equilibrium, charges are not moving. And be careful here. I don't mean electrons aren't whizzing around protons in atoms. I mean in bulk, there's no motion of charge. The electric field is, and I also mean, down inside the atom, there may be electric fields, but in bulk, there are no electric fields in a conductor in equilibrium. Now that means if I draw any kind of surface, I call these surfaces Gaussian surfaces because they're associated with Gauss's law, inside the conductor, the electric field is zero everywhere inside the conductor, so there are no field lines emerging from that surface. And what Gauss's law told us was that the number of field lines emerging from a closed surface depended on nothing but the charge enclosed. So there is therefore no charge enclosed by that surface by Gauss's law. Now I'm going to take that surface and I'm going to expand it till it lies just beneath the surface of this conducting material. The green blob is the conducting material. So there's no field lines inside, so there is no charge enclosed, and now I'm going to move that surface out. Put it just inside the material surface. There's still no charge within that. Our argument hasn't changed at all. There's still no electric field inside the material in equilibrium. There's no charge within that surface, and therefore, if there is any charge on this conductor in equilibrium, the only point it can be is on the outside surface of the material. And that's a very powerful statement. It says that charge on a conductor in equilibrium must go to the outside of the conductor. And you can kind of see why that makes sense. Because if I put positive charge on the conductor, the positive charge repels. It wants to run away from itself, and it wants to get just as far as it possibly can, and that's on the surface of the conductor. Now, that may sound almost obvious, but that's not alone a proof of this statement. That all the charge end up exactly on the surface is a consequence of the inverse square nature of the electric force, and Gauss's law, as I said, is equivalent to Coulomb's law and expresses that inverse squareness. So this provides really exquisite tests of the fact that that exponent in Gauss's law, in Coulomb's law, which is equivalent to Gauss's law, is exactly 2, or 1 over r squared minus 2 is the exponent. So there's a very elegant proof that if I have a conductor in electrostatic equilibrium, all the charge must live on the surface. That has very practical consequences, and here are 3 pictures suggesting what some of those consequences are. In the upper left, you see a car being struck by artificial lightning from some kind of particle accelerator. The driver inside that car is perfectly safe because the charge distributes itself on the surface of the metal car, at least if the car is made of metal, of a conducting material. On the right, you see a dramatic demonstration from a very large Van de Graaff generator. It looks like the one I showed you in the last lecture. I had a little one here. We charged up some balloons. This one is much bigger. It was originally a big particle accelerator. It's now a demonstration device at the Boston Museum of Science. There's an operator sitting in a metal-covered cage, and he's perfectly safe from that giant bolt of electrical spark because, again, the charge lives on the surface. More practically, you connect your stereo amplifier or your Netflix TV box or whatever to your TV with coaxial cables. Coaxial cables have a central conductor and an outer conductor, as you see here, consisting of kind of a braided conducting material. And again, the idea is any excess charge due to stray electric fields that might be wandering around and that would cause noise and interfere with your stereo and with your picture, they go to the outside and they live only on that outer conducting shield. So the whole concept of electrical shielding is the concept that in equilibrium, charge runs to the surface of a conductor and stays there. I have a colleague who does such sensitive experiments in her lab at Harvard that she has the entire lab surrounded by copper and very careful when any kind of wires or other connections have to go in there to preserve that without any break. And so there are no stray electric fields in there to interfere with very sensitive experiments. So let's wrap up what we've seen here. We have seen that electric fields provide an alternative to the action at a distance description of electrical interactions. We've seen how to draw field lines. We've seen Gauss's law for, in particular, in this case, a dipole, an important charge distribution we looked at, and tells us that the number of field lines emerging depends only on the enclosed charge. And in conductors, we've seen in equilibrium, any excess charge has to lie on the surface. Now, if you don't want to do a lot of mathematics, you're done at this point, but I'd really like you to take a look, if you do like doing mathematics, at a challenge I'm going to give you, and it's a challenge which will prove a statement I made during this lecture, a very important statement, in fact, about the inverse cube dependence of the electric field of a dipole. It's that inverse cube dependence that gives rise to a lot of the more subtle interactions between molecules, so it really is important in both physics and chemistry. So here's the challenge. Back in lecture 28, we did an example of a simple charge distribution to find the field on the perpendicular bisector, in that case of a line between 2 equal point charges. That's what we did in lecture 28, and I worked through it in all those details. And I'd like you to do the same thing, but now do it for an electric dipole, and do it by changing the right-hand charge in that example to minus q. So now you're going to have plus q and minus q, and you want to find out what's going on, what effect that would have either on a third charge or simply what electric field there would be there. And I'd like you to use your result to examine that special case we looked at before, the case where the distance to the third charge or to the point where we're evaluating the field is very large. And I want you to show from that the dipole field falls off as 1 over y cubed. So take a look at that problem and go to work on it, and let's then come back and look at the solution. Here is the picture, pretty much the same picture as I had in the previous lecture, except that now we've got a negative charge at x equals plus a. We've got all the same math we had before. And the only difference in this case is the direction of the electric field. And now I'm drawing field vectors rather than force vectors because we understand electric fields. And I haven't put any charge up at that point because I don't need to. I just need to evaluate the field and then ask what would happen to any charge put there. And you'll see that the net field is now pointing to the right because those two fields now, their vertical components cancel and their horizontal components add to give us a net field to the right, which is consistent with that picture of the dipole field that I drew for you before. The field went sort of parallel to the axis of the dipole, the line between the two charges, at the point right on the perpendicular bisector, and that's what we see happening here. Okay. So field is force per unit charge, so I dropped Q out of the picture. The net field is now to the right, and we can calculate the field. It's KQ over R squared. We dropped the big Q. And now the relevant trig function is the sine of the angle instead of the cosine. And you can see that because we're looking now for the horizontal components rather than the vertical components. And if I did the same kind of math I did in the previous lecture, we'd see that the sine of that angle is the opposite, a, over the hypotenuse, square root of a squared plus y squared. So there's our expression for the field. The distance r is still, again, square root of a squared plus y squared. We can simplify that by combining the denominators to make a squared plus y squared to the 3/2. And this expression looks very similar to what we had before, except that now we've got a upstairs instead of y. And what that means is, when we take y much, much greater than a, downstairs we've still got y cubed, but upstairs we don't have the y to cancel it, and consequently we see an electric field that falls as 1 over y cubed. So there's our proof, at least in one special case on the perpendicular bisector of a dipole, that the dipole field falls off as the inverse cube of the distance. And if you did a more complicated calculation, you would find that was true everywhere in the field of the dipole, although the exact value depends not only on how far you are from the dipole, but on what angle you make with the dipole axis. So dipoles are important because they're a metaphor for molecules, and this has told us something about the force of interaction between molecules, and it's weaker than the force of interaction between point charges.